Good morning, ya. Today I'm going to present the article entitled A Real-Value Mathematical Model of the Output Power in Power Amplifiers by Luis and Eduardo. This article has been divided in 6 sections. We will start with a brief introduction about power amplifier. Section 2 will review the complex memory polynomial, which is the basis of the model in this paper. In Section 3, the alpha model is reviewed, which will be used as a benchmark. In Section 4, we explain how the beta model was founded and compare the main difference between them. In Section 5, we will present the simulation results and explain how they were calculated. Finally, Section 6 will present the final conclusion about the performance of the models. Introduction. Radio frequency power amplifiers have become a key component in wireless communication. In this situation, we are looking for amplifiers that feature high efficiency and yet linear behavior. But as both are difficult to achieve, we need to find a balance between them. For this, it's important to use a model that is light and accurate. The purpose of this article is to present a mathematical model that, based on the amplifier's input, is capable of estimating its output power. The model was named beta and uses real coefficients as parameters. For comparison purpose, another model presented previously will be used, which was called alpha model and utilizes complex coefficients. Both models use the complex memory polynomial as a starting point, which adopts a black box approach. This approach does not worry about the physical details or what is inside the box, but only in the input and the output data of the system. Complex memory polynomial. To calculate the power amplifier output power, we need to find first its output. Once it's done, we can easily calculate it by applying the power formula, where P is the output power, Y tilde represents the output, and Y tilde to C power represents its complex conjugated. To model the power amplifier output given its input, we will use a complex memory polynomial, where X tilde is the input, P is the polynomial order, M is the memory order, and tilde B are the complex coefficients. Note that the output depends on its polynomial order and the memory order. For each combination of those, we will have not only a different output, but a different output power as well. We would like the output power model to be as generic as possible, but given the trouble in doing so, we limited the polynomial order to 3 and let generic the memory order. Alpha model. The alpha model is given by the following equation, where P subscript alpha is the output power estimated, and A tilde, B tilde, C tilde, and so on are the complex coefficients. This model already has been presented in a previous article and will be used only as a benchmark. Beta model. In spite of the fact that both models use the complex memory polynomial as their foundation, we derived in a new model named beta, where P beta is the output power estimated and A, B, C are the real coefficients. The main difference between the two models is that in the beta model, we open the complex coefficients in the polar format, as shown in the first equation. This change made possible the mathematical simplification presented in the second equation. Knowing that, we summarize the difference between the two models in 2 points. The first is that because of the coefficient data inside the cosine function, we have a nonlinear in the parameter model, different from previous model, which was linear in the parameters. The second is that because of the simplification, 2 coefficients were merged into one, reducing it by half, as shown in the following table. Note that all coefficients from the alpha model are complex, and all coefficients from beta model are real, so technically, both models have the same number of coefficients. But because a complex number is composed by a real and an imaginary part, each complex coefficient is equivalent to 2 real coefficients and that's what we are comparing. Results. Once the beta model was calculated, we were able to simulate it and evaluated its performance. In this case, since the model is a nonlinear in the parameters, to train the model and find its coefficients, a nonlinear optimization was performed. The entire program was written using the software MATLAB. To solve the nonlinear equation, the native function lsqnonlin was used. The data used in this simulation was from a power amplifier class AB that used a high electron mobility transistor fabricated in gallium nitride technology. The amplifier was excited by a carrier signal of frequency 900 MHz and modulated by a 3GPP double DCMA envelope signal having about 8.84 MHz of bandwidth. The measuring instrument was a Rode and Schwarz vector signal analyzer at the sampling frequency of 61.44 MHz. The data have already been processed and split to avoid any overfitting problem. The first part was named extraction and was used to train the model. The second one was labeled validation and was used to evaluate its performance. The criteria adopted to evaluate the model accomplishment was the normalized mean square error, defined as following, where n is the length of the vector, y half is the vector of reference, and y test is the vector that's been tested. The vector of reference was calculated applying the output power data in the power formula, and the vector that's been tested was calculated using the input data and applied it in the model equation, where the coefficients were defined in the training part. The results were compiled in the following table. Notice that for both models, the NMSE achieved was very close, and the big difference was in the runtime. Since the beta model is a nonlinear in the parameters, to train it using an optimization is more demanding compared to the alpha model, which is linear in the parameters. Conclusion. In this paper, we presented and validated the beta model. It was compared to the alpha model and showed a similar NMSE, ranging from -20 and 30 decibels, depending on the memory order adopted. Because of its linearity in the parameter, the alpha model can be trained much faster. The biggest advantage of the beta model is the running complexity. Because its simplicity and reduced number of parameters, once the model has been trained, it can estimate the output power faster. Finally, one of the main applications of the model can be the calculation of the amplifier efficiency, since for this, it's first needed to know its output power. The author would like to acknowledge the financial support provided by the National Council of Scientific and Technological Development under the program PBIT. Here we have all the reference used in this article, and thank you very much for your attention. I'm available to answer questions both in English and Portuguese in the following email.